So we've been talking a lot about energy in reactions. We can actually figure out how much energy is released or absorbed by objects when we're heating them up and when we're cooling them down. Mm-hmm. And by doing that, we can use this formula, Q equals MC delta T.
Looks like MCAT.
Yes. So we can use Q equals MCAT, and when we break it down, Q is our heat, or we've also been calling it the enthalpy. Mm-hmm. So we may see it both ways.
Well, remember that heat is not... It's not a temperature or something, it's energy. So heat is energy. It is the same thing.
Right. Let's see. We got mass, which is the M. We've got something new. We got C. This is the different C. This isn't our speed of light.
No, this is a capital C.
Right. Which is called the specific heat capacity. And that's a... characteristic of all matter, and what it is the amount of heat needed to raise the temperature of 1 gram of a substance.
So the C is this.
Right, that whole thing.
Okay.
So it's how much energy it takes to raise the temperature of something.
Right.
And different substances all have different specific heat capacities.
Right.
And then the last one we have, that triangle T. We've seen the triangle before.
Delta.
Right.
Yep.
Yeah, and the delta means...
Delta, delta, delta. Can I help you, help you, help you? Not so much?
No, I wasn't much of a Greek person, so...
Delta Airlines. Anyways.
Whatever.
Change.
Right. And then... T is temperature, so we're talking about the change in temperature. And we use this in something called calorimetry. Yeah. You know when you look on the label of your whatever your food is and it says however many calories?
Cheetos!
Right. So, and Cheetos usually have some ridiculously high number of calories. Mm-hmm. They figure out that value using calorimetry, and that's something we'll get to play around with in a little while. But this is kind of how it works. All right, so these are what some of our problems look like. We've got the heat released from burning alcohol is used to heat 100 grams of water. From 24 degrees to 39 degrees, how much heat was released from the burning alcohol? So we want to know, this is what we're going to use.
This is it wants to know heat.
Yep, so we want to know heat.
Which is Q.
Right. We want to know the mass. And the mass they gave us was 100 grams.
Mm-hmm. And then our delta T is going to be 39 to 24 to 39. So, but the difference in them is 15 if you subtract them.
Right, because when we're doing this, we're not concerned with what the temperatures were. We just want to know how much they changed by.
Right.
So you always, if you get the two temperature numbers, we subtract them. So, and that's what we did there. Mm-hmm. And then C, so then we've got our C, our specific heat of water, and in this case...
it was provided for us.
Yeah, so it is 4.18. Maybe the only one we'd have to memorize is water, but 9 times out of 10, we're going to get it.
It's going to be given to you.
Yeah. So when we take our numbers, let's plug them in. So we want to know Q. We've got our mass, which is 100 grams.
Right. So 100 times
C, which is 4.18.
4.18.
Times the change in the temperature, which was 15.
15.
And then we multiply all that together. The amount of energy released was 6,270 joules.
How do we know that? Oh, it's because we have a calculator here.
Right.
Hey.
We're also just fabulous.
We are fine leaving our temperature in Celsius, guys. Okay, because this isn't gases. And if you look here, it says Celsius. So we're good with Celsius, guys. So don't freak out or anything.
No kelvins.
No.
All right. Celsius is good. And we're not going to do anywhere we have to do any other grams.
No.
Okay. So basically, when we're using this, like I said, we're using calorimetry. And the intent of calorimetry, one is to calculate how much energy is in something like food. Mm-hmm. The other one is to determine the specific heat of a substance, like a metal. You get a metal, you don't know what it is, you can figure out the specific heat and use that as a
reference.
Yeah.
Makes sense to me.
And so basically what we have going on is law of conservation of energy, right? Energy is conserved. So
right.
if you're burning something, or if you are putting something cold into something hot,
right.
the amount of energy that is lost by one thing has to be the same as what's gained by the other thing.
Right.
Yeah.
Makes
So
sense to me.
what we end up doing when we're trying to figure out specific heat of something, we have to set the Q equals MC delta T
against itself.
Against itself, right. So we have an unknown metal that's 3.2 grams with a temperature of 130 degrees Celsius. We put it into 22 milliliters of water. We've got the initial temperature of the water, which is 43.5 degrees Celsius, and we've got the final temperature is 45. So
we said we wanted to do Q equals MC delta T, right?
Yeah, equals
MC delta T for our different substances.
Right, and so now we can start figuring out our variables like we've done in the past.
Okay, so we had a mass, 3.2 grams of our unknown metal, right?
Right. We're looking for the specific heat of that metal.
Okay, so I'm going to put a C.
Let's just put a C.
And my change in temperature goes from 130
to 45.
To 45, because we are going to finalize at the same temperature as the water is where we're going to end. Okay.
Right. So if we would get our difference, it is now when you're trying to do the change in temperature, you take the final temperature, the second temperature, so 45.
Oh, makes sense.
Minus the starting temperature, which was 130. So that gives us
negative 85.
Right.
Okay, so we can have negative changes in temperatures.
Yeah, because that just means it's cooling off.
Cool.
Now we do, believe it or not, have the mass of the water, because if you remember, a milliliter of water equals 1 gram.
1 gram. So this is the same thing as saying I have 22 grams.
Right.
Okay, makes sense.
In this case, it gave us the specific heat of water, our C, so that's going to be 4.186. And then our change in temperature from this one, the final temperature was 45. The starting temperature was 43.5, so that means our delta T was 1.5.
That makes sense as well. Okay, so I can do all the math here on one side and then the other. So let's do 22 times 4.186 times 1.5, which is 138.138. And if I multiply 3.2 times negative 85 on the other side, I have negative 272 times C. I cannot forget the C. I need to carry that down. Okay, if you want to put this in parentheses so that you can see that C is separate, you may do so. Okay, I need to get rid of the negative 272, so I'm going to divide by negative 272 to get rid of it. And my specific heat, or C value, is negative 0.508.
So we can't have a negative for specific heat capacity.
Right.
And so this is nice. We can just not include the negative.
Right. So it's actually technically a positive because since your metal was losing that energy, it would have had a negative value to start with, so it kind of cancels out.
Right.
So if you ever when you get a negative like this, just make it a positive and move on. Okay?
Right.
Yay.
That's it for us. Try the guided practice. See how you do. If you have any questions, let us know. Otherwise, we'll come back.
All that fun stuff. Bye.